Welcome to Ask and Learn.
We want to use the guidelines in this section to sketch the curve y is equal to x minus 1 over x squared. So they give us this laundry list of steps for us to follow, so let's just go through them one by one. So the first thing they tell us is we should find our domain of this function. So remember, the domain just tells us where the function is defined at, and so for rational functions, we just need to make sure that our denominator is not equal to 0. And so, well, x squared not equal to 0 would just mean x can't be 0, so that was pretty straightforward for us. I'm going to go ahead and write it underneath. So our domain is going to be all real numbers excluding 0, so negative infinity to 0, union 0 to infinity. The next thing they suggest that we find is our intercepts. And so to find the y-intercept, that is when x is going to be equal to 0, but that is excluded from our domain. So we know right away that we have no y-intercept. No y-intercept. And then to find our x-intercepts, we set the numerator equal to 0. And so, well, that would just be x minus 1 is equal to 0, add the 1 over. So we end up getting that our x-intercept is going to be the point 1, 0. Next, we want to determine if our function has any kind of symmetry. So periodic or rational functions are normally not known for being periodic, so we can just go ahead and skip checking that. But we can check to see if it is even or odd. So what we're going to do is go ahead and plug in negative x into f, or into y in this case, and see what we get out for our input. So that's going to be negative x minus 1 over negative x squared. So let's factor that negative out of the numerator, so that would be negative times x plus 1 all over, and then negative x squared should just be x squared. Now, this is not equal to f of x or negative f of x, so that means this is going to be neither even nor odd. So, neither. So there is going to be no symmetry for this one. Now, the next thing we need to check is for any kind of asymptotes. So, asymptotes. So we're already told that over here, this would be a vertical asymptote of 0. Because remember, that's just where our function diverges to positive or negative infinity. And when we divide by 0, that's essentially what we're doing. So x is equal to 0 would be our vertical asymptote. And now to find our horizontal, remember we would take the limit as x approaches plus or minus infinity of y. And you might recall from algebra, when the numerator is smaller than the denominator, this just goes to 0. So we'd end up with our horizontal asymptote being the line y is equal to 0. All right, so next we want to figure out where the function is increasing or decreasing, and if it has any local mins or maxes. So this is 2 separate steps, but I think we should go ahead and combine them into one, because we need the increasing, decreasing to determine local mins anyways. So local min slash max. So for this, we're going to need to know what y prime is. So let's go ahead and go to another page to do this really quickly. So I don't want to have to use quotient rule to do this. So what I'm going to do is divide x squared into each. So we'd have 1 over x minus 1 over x squared. Now when we take the derivative of this, it's just using power rule twice. So we have y prime is equal to, so it would be negative 1 over x squared plus 2 over x cubed. And then if we want, we can go ahead and combine that into one fraction by getting a common denominator. So it'd be negative x plus 2 all over x squared. All right, so let's go ahead and set this equal to 0 so we can find our critical numbers. So we get x is equal to 0. So we'd have negative x plus 2 is equal to 0, or x is equal to 2. So this might be our local min or max. And then remember, we also want any of the values where the function is undefined. And well, that would just be when x is equal to 0. So these are the 2 points we need to check for increasing, decreasing, or I should say, how we're going to break our intervals up. All right, so this here was 2 minus x over x cubed. So let's go ahead and write the numbers that we had. So we had x is equal to 0, x is equal to 2. And so remember, our domain is not even defined at x is equal to 0. So we don't even need to really worry about that being a max or min. But we will need this just to help us for our intervals. All right, so the first thing we're going to do, or actually, I should say this first. So we know that a function is going to be decreasing when f prime of x is less than 0. So this is decreasing. And we know a function is going to be increasing when its derivative is positive. So we need to just figure out where this is broken up. And so by breaking it up into its critical values like this, it'll help us. So let's pick a number smaller than 0 and plug it into here. So like let's do negative 1. So 2 minus minus 1 would be 3, and then negative 1 cubed would be negative 1. So negative, or 3 divided by negative 1 is negative 3. So that means it's going to be negative to the left of x is equal to 0. Now we pick a number between 0 and 2. So let's do 1. So plugging in 1, we'd get 2 minus 1, which is 1. And then 1 cubed is also 1. So it would be positive there. And then we plug in a number larger than 2. And doing that would give us, so let's do 3. So 2 minus 3 is negative 1, and then 3 cubed is 27. So negative 1 over 27 is negative, so it would be decreasing like that. So since x is equal to 0 is undefined, by applying the first derivative test here, we would know that x is equal to 2 since it's being increased into it and then decreasing after is a local max. Right. And now for where it's decreasing, so it's just where the down arrows are. So it should be decreasing from negative infinity to 0 union to infinity. And then after that, we will have the function is increasing just from 0 to 2. All right, so we have all of that now. And the last thing we need to do before we actually start graphing is find our intervals for concavity, as well as any points of inflection that we might have. So for this, remember, we need to know what our second derivative is. So let's go ahead and find that. So just like before, I'm going to use this to take the derivative because I don't like using quotient rule. So again, we'll just use power rule for each of those. So the first one would give us 2 over x cubed, then minus 6 over x to the fourth. And then we can go ahead and combine this into one fraction. And that would give us 2x minus 6 over x to the fourth. And now to find our possible points of concavity, remember we're going to go ahead, set this equal to 0. And so that would give us 2x minus 6 is equal to 0. Let's divide each side by 2, so we get x is equal to, or x minus 3 is equal to 0. Add the 3 over, so we get x is equal to 3. So this is one of our possible points of inflection. And then remember, we also want to make sure to look at points where this is not equal to, or where the denominator is equal to 0, which would just be 0. So again, it's going to be 0 and 3. So our derivative was 2x minus 6 over x to the fourth. And our possible points of inflection were going to be x is equal to 0, x is equal to 3. Now, x is equal to 0, again, is undefined. So we don't need to worry about this at all. So undefined for our original function's domain. Now, x is equal to 3, we can try to figure out if that is a point of inflection. So it's going to be the same thing as before. Points of inflection just mean we have a change in concavity. So we know that if the second derivative is less than 0, this is going to be concave down. And if our second derivative is larger than 0, this will be concave up. So just like what we did for the derivative, we're going to pick numbers on either side of how this rational function is partitioned. So let's do -1. So notice that anything I plug into x to the fourth is always going to be positive or 0. So we only really need to figure out if the numerator is going to be positive or negative. So plugging -1 into there, we get 2 times -1. So we get -2 minus 6, -8. So it's going to be negative over here. Now, when we pick a number larger than 0, well, this is going to give us, so let's do 1. So plugging in 1, we get 2 times 1, 2 minus 6, which would be -4. So it's still going to be concave down. And then we pick a number larger than 3. So let's just do 4. So 2 times 4 is 8, minus 6 is 2, so it will be concave up on the other side. So notice how we have a change in concavity around 3, so this would be a point of inflection. And then for concave up, concave down, so we said that it will be concave down to the left of 0, so -infinity to 0, union, and then 0 up to 3, and then it will be concave up from 3 to infinity. All right. Now, that was the last thing we needed to do, so we can go ahead and start sketching this. So let's go ahead and put a little grid down right here. So the first thing we should probably do is plot our intercepts. So we only had 1, 0. So that should be about here. We had no symmetry. We know that we have a horizontal and vertical asymptote at 0 for each. So y is equal to 0. We have 1. And then also x is equal to 0. We have asymptotes. We know that we'll have a max, or a local max at x is equal to 2. So 1, 2. So there's a local max somewhere around there, and then we also have a point of concavity at x is equal to 3. All right. So now let's think about how we can graph this. Let me go ahead and make this a little bit darker. So let's start from our x-intercept. So on this interval here, this would be in this portion here. So it's saying the function is increasing up till 2. So that means we're going to keep on increasing until we hit our local max. So we hit that. And then it says we start decreasing after that. So we keep on decreasing like this. And then we have this point of inflection at 3. So around here is going to start to change concavity. So it looks like from 3 onward, it is concave up, and before that it's concave down. All right, so now to the left of our x-intercept, so it's still supposed to be increasing. So it just keeps on going like this until we hit our intercept here. And now, to decide on what side we need to start on over here, then that means we're going to do the following. So we look at x squared because so our denominator is 1 over x squared. And so remember, this has the same in behavior on either side of it. So that means we should start on the same side like this, and we're going to just keep on coming up. It doesn't have any kind of inflection, min or max on this side. So the only thing we need to now do is get as close to our horizontal asymptote as we can as we go out to infinity. So I'll just go ahead and put a little dot here to say that's our point of inflection. This here is our local, and it's actually our just max all around. And that would describe just a quick little sketch of this. So if you wanted, you could go in and say what the local max is and where the point of inflection is. But if we're just sketching it, I think this would be a good place to stop.